with the cards, right? So the whole point of the hypothesis test is to see if your sample is unusual or not unusual. It can be two-tailed like the last slide, or it can be one-tailed here where only this part is what we consider unusual, and this is kind of all, close enough or not unusual. Usual. The null hypothesis says my mean is the same as everybody else's mean, right? So for example, with the cards, we said that my proportion of red cards is the same as every other deck. So we said it was 50%. Everybody on board? So that's a null hypothesis. It says that my deck is 50% just like every other deck out there. And then what happens is we take a sample. So we took a sample and we found 6 black cards in a row. Right? And we figured out the probability of that is really unusual. It's very, very unusual to get 6 black cards in a row if the deck is 50-50. So since we got something unusual, then we said, whoa, wait. My mean is not, or in this case, my proportion is not the same as everybody else's. My proportion is not 50%. Ms. Young, your deck is rigged. It's not 50%. It's something less than that. Does that make sense? So that was what happened. We ended up getting a really low number of red cards. So we were way over here, and we rejected the null hypothesis because we decided that our deck was different than the rest of the world's decks. So here's another example. Say I have a friend. He gives me a coin. He says, here's a coin for you. He gives me a little wink. He gives it to me. I flip the coin. I flip it 10 times. After I flip it 10 times, I have 9 heads out of 10. Okay. So first of all, my general assumption is that my proportion of heads should be the same as every other coin. What's the proportion of heads in a coin when you flip a coin? 50%. So I'm assuming that my proportion is 50%. All right, so let's see. Oops, not too far. Let's try to figure out what the probability of how unlikely it is to get 9 out of 10 hits. So everybody Google Rossman chance. You can do it on your phone or you can do it on your computer, either one. So Rossman chance, 1 prop if you want to have a little extra. Rossman chance, 1 prop. So has everybody Googled it? If no one has it Googled? Well, maybe you have to babysit everybody and check that you all have it. I mean, I'm going to check anyways, but use your phone if you want. It's fine. Google Rossman chance applet. Got it? What do you have, Ryan? Oh, okay. All right, so then pick the one. I think it's going to be this 1 proportion one here. So I'm going to click on that. Yeah, that's the one. All right, so here it is here. And probability of heads is what? What's probability of heads? 50. All right, great. How many times did I flip the coin? How many times did I flip the coin? 10. Make that 10. Everybody do that? Make it 10. Are you there? Or use it. Okay. Great. So 10, 10, 10 times. No. Never tosses 10. All right. Now, Everybody turn off animate. See where it says animate, turn that off or else it'll take forever. And then do it like, I don't know, 1,000 times or 10,000 times. Yeah, 10,000 times. That seems good. Everybody put in not number of tosses. Number of tosses is still 10, but we're going to do that over and over again 10,000 times. So number of repetitions, 10,000. Good?
Yes.
Is everyone where I'm at? Because I'm going to move on.
Yes.
All right. Hit draw samples. And you should have something down here at the bottom after you hit draw samples. Everybody have that?
Yes.
You already have it? Michaela, you have it? Yeah. Okay, great. Now, we're going to move over to, Omar, do you have it?
Yeah.
Okay. So now we want to do proportionate, so down here we want to count, get proportionate heads as extreme as 90%, right? Because we had 9 out of 10 heads. So make that proportion of heads greater than or equal to 0.90. And then hit count. I have 0.011. Angela, what'd you get? 116. Great. Zora, what'd you get?
0.0104.
Great. Alondra, what'd you get?
0.0096.
Good. Lauren, what'd you get?
0.0111.
Okay, so everyone's getting like roughly like slightly over 1%. Does that make sense? So here, again, remember my null hypothesis is that my coin is the same as the rest of the world, so it should be 50%. But we got about 1% of samples that had 9 or more heads in general, right? So the probability of getting 9 out of 10 heads, oops, you can't see what I did. The probability of getting about roughly slightly over 1% of them will have 9 or more heads. So is it, what's our guideline for unusual? General guideline for unusual?
0.5 or less.
5% or less. Is this unusual?
Yeah.
Yeah, so what is more likely, do you think? That we just happen to get lucky or, have this odd thing where we happen to get 9 out of 10 heads? Or do you think that my buddy gave me a strange coin? Strange coin. So what we would say is that, so here, since we've got something unusual, we would say that our mean or our proportion is not 50% like everybody else's. We're going to reject the null hypothesis because we got something, if it was true, then we sure got something weird if our proportion is 50%. So we would reject the null hypothesis and say that our proportion is different than everybody else's. Remember, the null hypothesis says that you're the same as everybody else. And we're saying, no, we've got something weird. I don't think we're the same as everybody else. We're different. So that's kind of what the null hypothesis is saying. Right? So the null hypothesis says that you are right here. We got something way over here. So we're saying we're not, our proportion is not there. Our proportion is something else on this side. So we're going to reject the null hypothesis and say that we are not there. Is that everybody on board? Okay. Please note that when we reject the hypothesis, it means either, it's two possibilities. Maybe my sample happened to randomly be unusual. Maybe my coin really is 50-50, and I just happen to be one of those 1 in 100 chances of getting 9 out of 10 heads. It's possible. Or the other possibility is that my sample really is different, and my coin really is weighted to come up heads a lot more than tails. All right. But again, when you get something unusual, that's when you reject the null hypothesis. Because it probably is not correct. So now you're filling in more notes. Alina, go ahead and read for me.
A statistical hypothesis is a claim about a population parameter which may or may not be true. Do you want me to go on?
Yeah, please.
The null hypothesis denoted by H
Not.
naught is a statement that the value of a proportion parameter such as proportion, mean, or standard deviation is equal to some claimed value. Example, there is no difference between two parameters.
Yep, that's good. So make sure you're filling in your notes with this information. It's in there a couple of spots. So the null hypothesis says that there is no difference. Null difference. Null means zero. Zero difference between two parameters. So if you and your friend, if there is no difference between your scores on the exam, that means your scores are what?
No.
The same. Your scores are the same. If there's no difference between them, your scores are the same. They're equal. All right, so the null hypothesis says that there's no difference between two things. In other words, they're equal. The null hypothesis is always, always, always equal. Always. The null hypothesis is always equal. We test the null hypothesis in that we assume it's true, and then we take a sample and see that if it's true, do we get something that kind of makes sense, or do we get something that's really weird? And if we get something really weird, then we're going to reject the null hypothesis. Like I do with my cards, right? We assume that my deck is a regular deck. And then we get 9 black cards in a row, and then we're like, this is weird, this is very unusual. We're going to reject the null hypothesis and say that, Ms. Young, your deck is fixed. It's not a regular deck. Make sense? Good. Great. So again, the null hypothesis is always, always, always
True.
equals. Not true. Sometimes it's true, sometimes it's false. But we assume it's true, but sometimes it's true, sometimes it's false. But it's always, always, always equals. Let's try it again. The null hypothesis is always, always, always equals. Thank you. All right. Nathan, go and read for me.
The alternative hypothesis denoted by H1 and HA is the statement that the parameter has a value that somehow differs from the null hypothesis. The symbolic form of the alternative hypothesis must use one of these symbols.
Greater than, less than, or not equal to. All right. So the null hypothesis is always, always, always what?
Equal.
Equals. So the alternative has to be a different symbol. Greater than, less than, or not equal to. Should be filling these into your notes, right? Okay, everybody do problem number 1 on the worksheet. Circle the statements that could be null hypotheses. Circle them. Box the ones that could be alternative hypotheses. Do it. So, I'm going to check in with your neighbors. 15 seconds if you want before I start randomly calling on people. All right, Noor, the first one, did you circle or did you box?
Circle.
Circle. Why? Because it's equal. Great. Angela, next one, did you box or did you circle? Box. Because it's not equals, it's greater than. Everybody on board?
Yeah.
If you don't remember the greater than, remember it's the little fish, right? The smaller one is the 43, the mu is the larger one. So the mu is bigger than the 43. Next one, Austin. Boxed. Why? Because it's not an equal sign. Great. Next, Diego. Boxed. Great. Molly.
Circled.
Circle, because it's equals. And the last one, Omar, have I asked you anything yet?
No.
Great. Omar? Box. Great. Good. Now, we're going to talk about tests. Two-tailed tests and one-tailed tests and other things. So, folks see how it says two tails on the left and on the right? Both tails are involved. So, H naught doesn't give you any information about the tails because H naught is always, always, always equals, so that doesn't change. But my H1 will change. So if I am not equal to something, that means I could be less than it, or I could be greater than it, right? So if you're not equal to, you could be either left-tailed, less than, or right-tailed, greater than, either one, so that's two-tailed. Make sense? So not equal to is, that's where you get the two-tailed from. And then we have left-tailed test, where all the alpha is in the left tail. It's not split up, it's all in the left tail. So that's why it makes a difference. Your critical values are going to be different between one-tailed and two-tailed, because with two-tailed, you're splitting your alpha in half in each tail. Whereas with one-tailed, it's all in one tail. So it's going to be, it's going to change the critical values. The left-tailed, I'm saying that my mean is less than everybody else's mean. It's over here. It's less than. So my mean, my mu is less than mu naught, the world's mu. So we kind of got two mu's going on. My average for my folks is going to be different than the general average for the whole world. Left-tailed. And then we have right-tailed, where all the alpha's in the right tail. And again, we're saying now my H1 is that my mean is greater than everybody else's mean. My mu is greater than mu naught, than the general world's mu. All right, so now I want you folks to write in here the ones that you have boxed, which are these guys. Above them, write either L for left-tailed, R for right-tailed, or 2 for two-tailed. The equals we can't say anything about because those are null hypotheses. They could be for anything, right? Because the null hypothesis is always equals no matter what the H1 is. It's the H1 that determines whether it's left-tailed, right-tailed, or not equal to. So everybody write in 2 or R or L